Hi everyone, so this is a review for Chapter 12 revision quiz. Chapter 12 is on heat conduction and thermal expansion. So based on the responses that I received here, we will be discussing question 3, question 8, question 12, 13, 14, 15. A total of 6 questions for this set of revision quiz. So let's proceed to the first question. Question 3. Question 3 states that you have a diagram being given, and this diagram has a composite rod, and this composite rod is perfectly insulated. So when you see the word perfectly insulated, you have to be aware that it will be no heat loss. Composite rod means by rod made of more than one material. Okay, so the thermal conductivity of the core is 3 times the thermal conductivity of its skin. So if you look at the diagram here, the inner center of the rod will be the core, and this outer layer between the insulator and the core, we call it the skin. And they tell you that the thermal conductivity of the core is 3 times the thermal conductivity of the skin. So you can say thermal conductivity is K. So the K of the core is divided by C is 3 times the thermal conductivity of the skin. So that's what this sentence means. So we have to convert things from sentences into mathematical expression. So that's very important. Key is thermal conductivity, and it's 3 times between the core and the skin. The cross-sectional area of the core is twice the cross-sectional area of the skin. So cross-sectional area is what we are comparing right now, and the core is twice of the skin. So cross-sectional area, we represent it with the symbol A. So the A of the core is twice the A of the skin. Okay, so when both ends of the rod are fixed at constant temperature difference, it means by both of let's say this is the hot side, then this is the cold side, then both the core and the skin will face the same hot temperature at one end, and they will face the same cold temperature at another end. So the temperature difference between the two ends will be the same for the core and the skin. So temperature difference is the same. That will mean by delta T of C, the core will be the same as delta T for the skin, which is S. Okay, so with that said, what's the rate of heat flow through the core? No, they say that the rate of heat flow through the core and the skin are X and Y respectively. So rate of heat flow, we usually represent it as dq over dt. So they say the dq dt for core is represented by X, and the dq dt for skin is represented by Y. So I think I forgot to type the question statement, but basically you know what it is trying to find. It's trying to find a relationship between the rate of heat flow of the core and the rate of heat flow of the skin. So they are comparing X and Y. So the thing is, how should we compare this thing? Okay, we know that what can we do here is they tell us something about the relationship for thermal conductivity, and they tell us something about the cross-sectional area, and they tell us something about the change in the difference in temperature between the two ends. So I think if you see these three things and you see they ask you to compare dq dt, for sure you know that this equation will be used here. dq dt equals to Ka delta T over let's call it length also can. Okay, let's just call it length. Some people call it x, some people call it length. As long as you know what's the idea, then it's fine. Okay, so with this situation here, you need to compare this equation. You need to compare it for the core and the skin. So let's try to do it right now. So let me zoom it out a little bit. Okay, so what can we do now here is, let's try to build the equation for skin. Skin, probably easier to build equation. Okay, so dq dt for skin is equals to negative thermal conductivity of skin, the cross-section area of skin, a change in, not the change, the difference in temperature of the skin, and the length of the skin. So is there anything that we need to fix? Yes, we need to change dq dt of skin. You have to change it into the symbol that they use to express this thing. So it will be y equals to negative ks as delta ts over ls. So now what about the core? The core is dq dt of the core equals to negative k core area core difference in temperature core against length of the core. So now probably if we change everything to ks, then we can make a simple comparison between the two things. So what we do now is change everything to be expressed in terms of s. You have to express both equations with the same variables. Only you can make appropriate comparison. So if something is in s, something is in k, you have to choose one of them to standardize. So in this case, we standardize everything in terms of the quantity for skin. So we change KS, we change KC to represent in terms of KS. We change AC to represent in terms of AS. Delta TC, we change it to in terms of delta TS. And length of C, we change to express in terms of LS. So the equation is all over here. The relationship is all here. So it's a matter of substitution. So dq over dt for core is just x. So it's negative. Kc is 3ks. AC is 2as. Delta t from both of them are the same. So I express it in terms of delta s, express it in terms of s as well. Then this one will be in ls. Okay, so now if I do a bit of move around, 3 times 2 equals to 6. Then I have my negative ks as delta ts over ls all in the bracket. So as you can see here, everything here in the bracket is exactly the same as what we find here. So we can change it to be expressed in terms of y. So now x will be equals to 6y. So with that said, we have found our answer. Our answer is this. So what does this mean is our core has a greater rate of heat flow. Okay, our core has a greater rate of heat flow because our x is 6 times larger than y. So this one has a greater rate. So heat flows faster through the core compared to the skin. So the skin transfer heat slower compared to the core. So that's the idea of this equation here. So that's all for question 3. Let's move on to the next question. Question 8. A figure is shown here. So you have bar x and bar y, I think. So the figure shows 2 bars of equal length and same cross-sectional area. So when you see they say equal length and they say same cross-sectional area, but different thermal conductivities kx and ky. So it's a big bunch of words. So let's just break it down into mathematical expression. Equal length, so means by the length of x should be equal to the length of y. same cross-sectional area, so A of X, okay, it's capital X, have to be careful, equals to cross-sectional area of Y. And they say the thermal conductivity is different, so you don't have a particular relationship, so you just write it down like this. Then being joined together end to end is one end, the end of X is connected to the end of Y, so end to end. So one end of the composite bar is maintained at temperature Tf, whereas the opposite end is maintained at Th. So as they mentioned here, this one will be Tf, this one will be Th. Okay, so if there's no heat loss from the sides of the bar, so no heat loss, you have to understand that when there's no heat loss, it means by it's perfectly insulated. So when things is perfectly insulated, only your equation for thermal conductivity works, okay? Because it's a linear line for your Tx graph. Okay, so how would you solve this equation? They want to ask for the temperature G. Okay, this is what they are looking for. Temperature G. So temperature G, if you see here, temperature G is the temperature at the junction. Junction means by the connection point. Okay, so they are asking for the temperature at the joint area, at the junction. So what should we do then? Okay, so when they say this is perfectly insulated and they ask us to find temperature, when they ask us to find temperature, usually we assume things to be in steady state already. It means by Tf remains at Tf, Th remains at Th, Tg remains at Tg. Every point along the bar, even though they have different temperature along the bar, but every position, their temperature remain constant. If it's 80 degrees here, then it's 80. If it's 80 degrees Celsius here, then it's 80 degrees Celsius here later. It won't change. If it's 30 degrees Celsius here, then later it will still be 30 degrees Celsius. No change in temperature for every position along the composite bar. Okay, so if there's no temperature change, so we know that it is in steady state. So when it's at steady state, the rate of heat flow is constant all across the bar. That means the rate of heat flow at X is equals to the rate of heat flow at Y. Why this equation works is because this thing is now in steady state. Why do you know this thing is steady state? Because they are asking something about temperature. If you are asking something about temperature, you have to let the temperature not changing with time. You have to make the temperature an unchanging property against time. The temperature cannot change against time. Only you are able to find the temperature in this situation. Or else, if the temperature keep changing with time, what temperature are you finding? Halfway, at the end, middle? No. Okay, we don't want the temperature to change. That's why we have to assume that it is already in steady state. Okay, things have stabilized. So in that situation, what should we do? As usual, we know our equation. We have been given L, A, K. Well, it's the same old equation. So there will be negative Kx Ax delta Tx and Lx, whereas this one will be negative Ky Ay delta Ty Ly. So what can we do now? We know that Ax is equal to Ay, so that's a convenient thing to eliminate. And we know the negative sign are both here, we can just eliminate, and the length are the same, so we can eliminate. So we are left with Kx delta Tx equals to Ky delta Ty. So what now? Well, we know that we want to find something called Tg. And now you have no such thing in your equation now. So you have to put in Tg to replace something else. So we know we can still break this down. This delta T here is a difference in temperature at two different ends. So probably you can further expand it to write down the actual difference in temperature. So for me, I usually take, oh, there's no cold, there's no hot. So you just need to be consistent. For me, I will take the right hand side minus the left hand side. So if it's x, then I'll take Tg minus Tf. So for bar y, then I will take Th minus Tg. I take the right hand side minus the left hand side. Okay, you have to be consistent or else there will be sign error. Okay, so now we want to express everything in Tg. Now it's just maths. You open everything up because you want to arrange Tg at one side of the equation. Okay. So now bring Tg to the left hand side. So you have Kx Tg plus Ky Tg. Then you bring the other stuff to the other side. So you have Kx Tf plus Ky Th. Now you know that there's two terms with Tg on the left. So you can factorize out Tg. Then there will be Kx plus Ky. And that will be equals to Kx Tf plus Ky Th. And now it's the matter of substitution. So Tg will be not substitution, it's just algebraic. So you just bring everything to the right hand side. Tada! So that's your answer for Tg. So it's just algebraic manipulation. So if you are okay with algebra, right, you slowly move through it, eventually you'll get the answer. It's a matter of being confident with your mathematical skills actually. Okay? But of course it can be improved through a lot of practices. So the answer is D. So that's all for question 8. Let's move on to the next question. Question 12. The graph shows the change of temperature along a composite rod which consists of three materials P, Q, and R of the same dimension. So if they say of the same dimension, the first thing that you should pop out in your mind is they have the same length. So length of P is equal to length of Q is equal to length of R. Okay, there are three composite rods here. This is the three composite rod and they have the same length and they have the same cross-sectional area. So the A P will be equal to the A of Q will be equal to the A of R. Cross-sectional area all the same, length all the same. Now they say the thermal conductivity of PQR and 240, 600 and 150 watt per meter per Kelvin. Okay, that's a lot to swallow. So, well, let's copy it down then. So thermal conductivity represented with K. So K of rod P is 240 watt per meter per Kelvin. K of Q is 600 watt per meter per Kelvin. K of R is 150 watt per meter per Kelvin. So these are the three thermal conductivities. So now they say the rod is perfectly lag. Okay, perfectly lag, you probably see in a lot of the questions already. Perfectly lag means by perfectly insulated. So no heat loss. Okay, because it's perfectly insulated, because it's having no heat loss, that's why you see all three lines here to be linear. It's linear because there's no heat loss. Okay, that's the characteristic of the graph. If there's heat loss, then the bar will have less heat then above have less heat, so for sure the temperature will be lower than the perfectly insulated case. Okay, so that's the idea for perfectly insulated, perfectly black. And the ends are maintained at 95 degrees Celsius and 20 degrees Celsius respectively. So they are saying that the hotter end is 95, the colder end is 20 degrees Celsius. Okay, so which of the following arrangement represents the composite rod? So this question is quite fresh. You need to know, what you need to do is you need to arrange whether P comes first or Q comes first or R comes first, then followed by Q or R or followed by P, or yeah, you get what I mean. Okay, so what should we do now then? Okay, again, they are talking about temperatures and they are able to give you temperature distance graph. If they are able to give you temperature distance graph, means by the temperature at all points here are already fixed already. The temperature will no longer change in time. Means by the next second you will not see another graph. 5 minutes later you will still see the same graph. So the temperature at different position, even though they are different, but they are remaining constant. Each position, their temperature remain constant, even though at each position, their temperature is different. So this situation, we understand it to be steady state. The temperature at each position remains the same. The temperature has become steady state. So now we know it's steady state. We can reasonably use this formula now. The rate of heat flow for rod P is equals to the rate of heat flow for rod Q. Okay, we seldom do this, but for now we are just doing it for the sake of comparison. So dq dt, we can connect it together into one equation, so PQR. So now if you want to break it down, okay, let's just remove the negative sign. Okay, we all know the negative sign is there, we can just remove it. So it will be thermal conductivity of P times, okay, you know there's length, you know there's cross-sectional area, but they are all the same. So you can just get rid of it straight away. Okay, there's A here, there's a length here, but you can just remove it because you know they are all the same for P, Q, and R. So let's just do things a bit quicker. So we know what's left here is just change of temperature of P. So the same thing, you'll notice will be thermal conductivity of Q with change, not difference in temperature. Ouch, I'm saying change a lot. It's not change. Change means that over time it changes from one value to another value. This is not change. Nothing is being changed. This is the difference between one end and another end of the rod. Okay, this is the difference between the ends of the rod, the temperature of the ends of the rod. So yeah, I have to be more careful with my usage of language. So KR, then this one will be delta TR. So we know the values, so we can probably do a little bit of ascending, descending order things. We know that KR is the smallest, followed by KP, followed by KQ. KQ is the largest. Okay, so let's see. If K delta T is constant, if you have a larger K, if you have a larger thermal conductivity, what will happen is, to make this value constant, you are not increasing K delta T. K delta T should remain constant for all three of these because they remain equal. You want to equal all these things, means by if you have a larger Kp, you need to have a smaller delta T. Okay, it's not increase or decrease. Sorry, I should make things very clear. It's not increase or decrease. All of these, the P, the Q, and the P, the Q, and the R are all equal. So if they are all equal, if you have a larger K, what will need to happen is you need to have a smaller delta T. And if you have a smaller K, you need to have a larger delta T. So when you multiply these two terms together, they will be the same for P, Q, and R. a larger k should match with a smaller delta t. A smaller k should match with a larger delta t. So with that said, we can know that it's an inversely kind of relationship. So you know that the delta t for q should be smaller than the delta t for p. It should be smaller than the delta t of r. So we can build this relationship. You can see that it's now the opposite sign. It means by it has an inverse kind of relationship. So now we know that delta t of r is the largest, delta t of q is the smallest. So if we look back into the graph here, this is delta, not d. This is delta t of 1, this is delta t of 2, and this is delta t, no, there's one more. Sorry, I've been a bit blur now. This is delta t1, this is delta t2, this is delta t3. So as you can see here, the smallest one is delta t2. Smallest one is delta t2. So you say this one is delta t2. So the biggest one is delta t3. So this is delta t3. So then the middle one will be delta t1. Okay, so now we can match to say that delta t3 is actually delta tr, delta t1 is actually delta tp, delta t2 is actually delta tq. So now we know that this 1, 2, 3 is actually just 1, 2, 3. So from here we can do a bit of matching. Then we'll say 1 is for p, 2 is for q. Okay, we are looking at here. 1 is for p, 2 is for q, and 3 is for r. So now this will be r over here. So now we know our arrangement will be p, q, r. Okay, therefore the answer is this. Okay, so the key to unlock this question, right, it should be you need to figure out that if you are given a temperature distance graph, it means by the temperature doesn't really change with time. So we can say it's in steady state. So when it's in steady state, then you know that the rate of heat flow for P, Q, and R will be the same, because that's the properties of something in steady state. And from there, you can start to build relationship, compare probably in ascending or descending order or any kind of comparison. Then from there, you infer what will be the change in temperature for P, Q, and R. Then slowly do a bit of matching, then you can get the answer. There's many ways to do this question as usual, but as long as you know what you're doing, as long as you start with this, then probably you'll be fine. Okay, so that's all for question 12. Let's look at the next question. Question 13. So the question 13 here says the figure shows two metal rods of length 30 cm and 10 cm respectively. So you can say the length, okay, length of M is 0.30 meter. Actually convert into SI unit. Length of N will be 0.10 meter. And the cross-sectional area for both rods are the same. That will be AM equals to AN. Cross-sectional area is the same. And they join end to end as shown. Okay, so this is a picture, this is a diagram showing M and N connected together. So the rods are perfectly insulated. When you see the word insulated, the thing that should pop up in your head is no heat loss. So if no heat loss, then your equation can be valid. This equation can only be valid if there's no heat loss. Okay, it's important to be aware of that because of this delta T over X here. Delta T over X here is actually, you are saying that the line, this is temperature X graph So this will be delta T. This will be X. So you need to have a straight line here. Only you can use this equation. So for you to have straight line, linear line, you have to have no heat loss. Because if you have heat loss, then the line will not be straight anymore. So if you want to have no heat loss, you must be perfectly insulated. Okay, that's why your line must be linear. That's why your graph must be linear graph. Okay, so the rods are perfectly insulated when steady state is achieved. So they mention it steady state again. So steady state characteristic is dq dt is constant all along the rod. Okay, the temperature of the junction is 40 degrees Celsius, it's stated here already. So the ratio of the thermal conductivity of M to N is, so they ask for the ratio of thermal conductivity and they ask for M to N. That means you have to find the ratio of Km to Kn, which usually in physics we just write as Km over Kn equals to what? Okay, so now if you notice, this question is exactly the same in terms of structure of the question if you compare with your tutorial question number 4, I think. Yeah, question number 4. Question number 4 of your tutorial chapter 12, the structure is exactly the same. And I have done a video explaining question 4 in a separate video. So if you have question, if you still cannot solve this problem, even with all this value extracted, what you should do is you should watch the video, try to understand it, then replicate, or you try to imitate how we do the question there, here. Okay, the structure is exactly the same. So give it a try yourself. So we move on straight to the next question. Okay, question 14, before I straight away and start, first I'd like to apologize. If you see here, the sentence here is a bit weird. That's because I wrongly typed the question. Okay, I forgot a few words inside, not a few, it's actually I forgot a lot of words. So this is a newer version. Okay, please have a read at it first. I probably zoom it larger because this is the first time reading it. So read this question first, then after that we will solve it together. Okay. Let me zoom it out a little bit. Question 14. A room has concrete walls of width Y. Oops. Width is Y, then thermal conductivity is K. So this is mentioned, we are referring to the concrete wall. The concrete walls has width of Y and thermal conductivity of K. The temperature outside the room is 32 degrees Celsius and the temperature inside is maintained at 26 degrees Celsius by an air conditioner. So air conditioner is actually aircon, the thing that you really love. So to represent the situation better, let me draw a situation. So you have a wall, you have a room, then the room is made out of 6 walls forming a room. So they also tell you that this room has a specific width. Okay, something like this. So they now tell you that the width is Y and the thermal conductivity is K. And inside the room it's 32 degrees Celsius. No, inside is not 32. Outside is 32 degrees Celsius. Inside is 26 degrees Celsius because you have a nice cold aircon. Okay, aircon. So when the inner surface of the wall is fully covered with a wooden layer, okay, now you have a wooden layer, someone doing renovation, so you have a wooden layer an increase. Oops, it's not like this. It's supposed to be a rectangle. So wooden rectangle. Something like this. Okay, so you have an additional layer of wood, and this wooden layer caused the combined thermal conductivity. Yeah, I write it down there. The combined thermal conductivity is now 0.84 K. Before that it's K, now it's 0.84 K, and the width of the wall, the width of the combined wall, it's now 1.4 Y. So the width, of course, you add something, the width will increase. Okay, but now the thermal conductivity decreased. So now it conducts heat poorer right now. Before that, it conducts heat better, but after adding the wooden layer, the thermal conductivity decreased, so it conducts heat poorer right now. Okay, so now they say when the thermal conductivity change, when the width change, the temperature is now maintained inside the room. Temperature in the room now is theta. So you have a new theta as your new temperature inside the room. So if the heat flows occurs through the walls only, it means by there's no windows, there's no other kind of possible way for heat to flow, only walls only, and they are at the same rate. It means by before this, heat is flowing in with dq dt initial, and after you make some renovation, you have a new dq dt final, but they are saying that this dq dt initial and dq dt final, they are just the same. The heat flow is still the same. So you can say that dq dt initial will be equals to dq dt final. So now they ask for the value of theta. So well, since we already write that the rate of heat flow is the same, it is in steady state, well, let's just do what we have been doing all this while. So you'll have your K A delta T over length. Okay, but now the final, you have new condition, so let's just call it K prime A prime delta T prime over L. I dropped the negative sign. I was thinking whether I should drop it or not, but let's just keep it there because that's our formula. So now let's express everything in terms of the old quantities. So if you do a bit of expression right now, then delta K will be equals, not delta K, K prime will be equals to 0.84 K. So now it will be 0.84 K. Then the area remains the same. You don't change the area of the wall. The area of the wall is still the same. So A. So delta T will be different now. So let's just continue right as delta T prime. Then the length of the wall is now 1.4y. Okay. The old situation, you also do the same thing. Negative Ka delta T over y. So now there's something that we can cross out. We can cross out the Ka, we can cross out the y. Okay, they are on both sides. So now we cross out the negative sign as well. So now you are left with the original change in temperature is equals to 0.84. 0.84 divided by 1.4 times the new change in, not new change in temperature. No, it's not change, it's difference in temperature between the outside of the room and the inside of the room. Now I'm being angry with myself already. It's not change, it's difference. Okay, so now what can we do is just substitute in the value. Just now we say the hot is 32, the cold is 26. I usually take cold minus hot because there's a negative sign, so I usually keep it consistent, the cold minus the hot. So now it will be 26 minus 32. Okay, but if you're being very careful, you can change it to Kelvin first. instead of degrees Celsius, change it to Kelvin, only you do the difference in temperature, you still get the same answer. So I just keep it in degrees Celsius. So 0.84, 1.4, then you have 32 minus the new temperature inside the room is theta. So now if you shuffle everything around, you end up with answer of theta equals to 22 degrees Celsius. So the new temperature in the room is 22 degrees Celsius. Therefore, our answer will be 22 degrees Celsius A. Okay. So this is the situation. Okay, so let's move on to the next question. Question 15. In the following diagram, J, K, L are conductors of equal cross-sectional areas, and the thermal conductivities are 3K, 5K, and 2K respectively. So let's just write it down. The thermal conductivities for J is 3K. The thermal conductivity of K is 2K. The thermal conductivity of L is 2K, 3K, 5K, 2K. This one is 5, sorry. Okay, the temperature difference T between P and Q is constant, but it shouldn't be T. It should just be delta T, then it matches better with our understanding. But now they are saying that the delta T from the NP to NQ is equals to T. This is what they are saying. So the temperature here, you compare with the temperature here, the difference is big T here. Okay, and they say that the temperature as P is higher than Q. So this one should be the hot, and this one should be the cold. Okay, the rods are perfectly insulated. Once again, you see the word perfectly insulated, no heat loss. So this dt dx thing here is linear. Only if it's linear, only you are able to do what we are doing later. Okay, so what is the temperature difference across the rod J and L? So they are asking from here to here, how much temperature difference? From here to here, how much temperature difference? So before we start to say anything about this question, this kind of question is explicitly stated to be outside of syllabus. Okay, your syllabus only asks you to do heat conduction that involve at maximum 2 rods connected in series. Okay, we are not allowed to ask you rods more than 2, but this is just me adding in to create a little bit more fun, probably. Yeah, fun is a bit subjective. I think it's fun, so let's try it. So again, we assume everything in steady state. Yeah, the reason is explained in the previous question. Delta Tj, let's say is equals to, not let's say, it's equals to delta T dq dt of K. So now let's, we know we want to express everything in terms of T, right? Want to express everything in terms of T. So later when we expand it out, then it will be negative Kj Aj delta T of J against L of J, right? And this one will be equals to negative K of K, A of K, delta T of K, and Lk. But we see that our answer here requires us to express everything in terms of this big difference in between P and Q temperature. So what I would think is I'll probably change things up a little bit, and I'll express difference in temperature at the for rod J to be equals to J times T. So it means by this temperature difference between here and here is equals to a ratio of from something from here to here. So J here represents a ratio. Okay, J here represents a ratio. Okay, so again, I will also do the same thing for K. So K will be equals to K times T. I will try to express everything in terms of ratio, in terms of T. Okay, I will express everything in terms of T. Okay, so now delta T of L, the difference in temperature at rod L will be equals to LT. Okay, so I express everything this way, then later our answer will be easier to be obtained. So now I can change things up a little bit, maybe. So first thing first, I remove the negative sign. That will make things easier. Then I believe the area are the same, equal cross-sectional area. Then I can remove the K, the A, and yeah, so that's what we have now. So let's substitute everything that we have in. We know Kj is equals to 3K. We express delta Tj, the difference in temperature at rod J. We express it in terms of J and T. T is the temperature difference across the whole rod. Then the length of J is just X. Okay, then we equal it to Kk is 5K. Then we express things in Kt over length of K is 3X. Okay, now you see a lot of things are repeating here. So let's try to remove some stuff. Again, you see K is the same, X is the same, T is the same. So now you are left with 3J equals to 5 over 3K. So it's just a bunch of numbers being compared. So let's just say J is 5 over 9 of K. If you express things in K, probably make things easier. So now we have done it for rod J and K. So now let's do it for K and L. So how do we do it for K and L? We do the same thing as well. dq over dt for rod K equals to dq over dt for rod L. Then this will be equals to negative kk ak. I'm a bit tired of saying all these kp, all these things. Lk. And this one will be equals to negative kl al delta tl over ll. So that again we can remove the negative sign, remove the area, they are the same. So let's do substitution. Kk is 5k, so delta tk we change it to kt, then over lk is 3x. Then kl here it's how much? 2k. TL, delta TL expressed in terms of LT. Then L of L, length of L, represented in half of X. If you're not sure where I get my length, it's all in the diagram itself. Okay, so again, we got many things to remove. We got KT and X to remove, KTX. So now we are left with 5 over 3K equals to 4L. Well, we express things in K, we express J in terms of K, so let's just express L in terms of K. So if we express L in terms of K, it will be 5 over 12K. Okay, now we are stuck. So what should we do now? We should acknowledge that this thing JT here plus KT here plus LT here should actually equal to T, because the change of temperature at rod, the difference in temperature for rod J plus the difference in temperature for rod K plus the no more plus already. Okay, then you end up with difference in temperature of rod L. You add them all up, then what should come out is it should be the total change for PQ. So total change for PQ is equals to T. So now we know that t is actually just 1t. So we can see here that, okay, let me move this a bit to the side. Okay, jt plus kt plus lt is equals to 1t. So we can factorize out the t, and there will be j plus k plus l equals to t. So we can remove the t on both sides. Then we know that j and k and l, if you sum them up together, it will be equals to 1. Okay, so we have j plus k plus l equals to 1, and we express everything here, j and l, we express everything in terms of k. So it's probably a good idea for us to find what's the value of k. Then we can substitute the value of k here and can get the value of j. Then it's just a matter of substitution here, then we get our answer. Okay, we are not sure what's the answer, so let's try. So j is 5 over 9 k. So j is 5 over 9 k. That's here. K is just k, don't change anything. So L is 5 over 12k. They all equals to 1. So let's factorize out k, then it will be 5 over 9 plus 1 plus 5 over 12 equals to 1. So now if you bring this thing to the other side, what will you get? I'm calculating it with you as well. So your answer will be 36 over 71. So this is the value of k. So now we can say j is equals to 5 over 9k, which is equals to 5 over 9, 36 over 71. This will be 1, this will be 4, 5 times 4 is 20, so it's 20 over 71. So this j here is 20 over 71. How about L? Want to find L as well? Because the question is requesting two things, j and L. So L will be equals to 5 over 12k. If you're not sure where do we get this thing from, it's from here. Okay, we are talking about these two equations, and we are substituting the k into these equations. So it's equals to 5 over 12 times k. K is 36 over 71. So this will be 1, this will be 3, 5 times 3 is 15. So it will be 15 over 71. So this L here, it's 15 over 71 of the total difference of temperature between the whole composite rock PQ. Okay, so it's 20, then it's 15. So we look for our answer here. Do we have it? Yes, we have it. Our answer will be this. J is 20 over 71t. L is 15 over 71t. Okay, so that is the answer for question 15. It's a very long-winded way of doing this thing. I definitely am confident that there's a simpler way to solve this. Just that I didn't have time to think through it, how to solve it simpler. Okay, so but that's it for question 15. So is there any next question? No. Okay, so that's all for set 1. Thank you very much.